Okay, thank you for the introduction. Well, you already said it. I'm Francisco. I work for CERN in the Communication Systems Department. It's group, which is part of the IT department. I'm going to start giving a bit of context about what CERN is, in case you haven't heard of it. What are the network and telecom services that we provide, and then I'll move on to what we have today and what we plan to introduce in the network services. Is it working? Yeah. So about me, I'm from Spain. I'm living in Geneva and working for CERN since 2013. I'm not a physicist, so you shouldn't be asking me questions about the Higgs boson or particle collisions. And previously, I have been working in Spain as an NGN IMS core network engineer for Telefonica, Huawei, and Vodafone. So about CERN, it's an international organization that is next to Geneva. It was founded originally by 12 countries, and now we have 21 member states. It's a really great example of what can be achieved when people collaborate, and it's we're somewhere between the borders. So you can see that this line over here, this is the frontier between the border between Switzerland and France. So only a small part of the LHC ring, which is our most well-known accelerator, it's under the Swiss territory, so most of it is under the French one. That causes a lot of issues regarding roaming coverage for the telecom services, but otherwise it's a really nice place to work, and we cover an area that is bigger than 60 square kilometers. So we have just one goal. It's quite simple. It's understand the universe, how it is made, and what is it made of, and how does it work. For that, we have a complex series of accelerators that will, from the linear injectors over here, we'll get the protons, we'll accelerate them until 99.9999% of the speed of light. And then they will collide in these points over here, CMS, ALICE, LHCb, and ATLAS, which are the experiments that are the detectors that they are like big photo cameras that will take a picture of what happened in the collision. So the LHC is the biggest of the accelerators. It covers 27 kilometers of circumference. It's around 50 to 175 meters underground, so it's not on a even plane. And the energy of the collisions is around 13 tera-electron volt. That's around the same energy that a train traveling at 200 kilometers per hour has, but the thing is that it's on a really small surface. So they are really, really heavy impacts. And these blue things that you see over here, they are this is one of the 1200 supraconductor magnets, and all this is covered with cryogenic pipes that need to be at around 2 Kelvin degrees, so that's the same temperature as outer space. And then we have a magnetic field of around 8 Tesla, which is 100,000 times the magnetic field of the Earth, so it's quite powerful. We did an upgrade to increase the energy, so now the collisions are taking place more frequently and with more energy. So this is what it looks like a bit on the underground part. There are 4 main experiments. ATLAS and CMS, they are the ones that were used for detecting the Higgs boson. The other 2, this is a quark-gluon plasma detector, and this one is, I think it's about neutrinos, but don't ask me too much. And then regarding the people working at CERN, we normally have around 12,000 people at CERN. Only a small part of them are CERN staff. The rest are visiting scientists and contractors. There are 2 people working at CERN that got Nobel Prizes, Carlo Rubbia and George Charpak. And in 2013, we had a crucial contribution to the Nobel Prize. That was the CERN control room. It's a huge room full of screens that are controlling all the cryogenic and all the LHC control systems. That's our DG. She started last year. She's from Italy, Dr. Fabiola Gianotti. And that's Tim Berners-Lee because CERN is the place where the World Wide Web was born. He came up with the idea of sharing files for the experiments at CERN. So for the networks, we have different network domains for administrative, for physics, so the traffics are separated. And then also for external traffic. Okay. We have more than 180 routers in our backbone, and we have an internet exchange point. We have around 400 points of presence inside CERN, and we have normally around 75,000 active users, and we don't enforce any operating system or device, so we will have a huge variety of them. We have been implementing bring your own device in a long time. And then we have the LHC computing grid, which is a worldwide grid that first takes the data from the experiments that are generating data at a rate of petabytes per second. But then there's an online system which will discard only the collisions that are interesting for the physics. So then, I think this is no longer correct, but I don't know the exact figure. But the idea is that we are the tier 0 of this grid, and then we will distribute all the data to the tier 1, which are major research centers around the world, which in turn will have a lot of different tiers underneath. And eventually we are now implementing volunteer computing, where you can install something on your workstation and you can help CERN compute some of the data. In terms of telecom and radio, we have a contract with a Swiss operator that is providing us the outdoor coverage, and for indoor, we inject it in the tunnel. So actually, we managed to have 2G, 3G, and 4G signal in the tunnel. We have a closed VPN for 6,000 users, and in total, there are around 70 radio sites. And in the tunnel, we inject the signal with this leaky feeder cable that is on top of the LHC. And we have more than 50 kilometers of it. And then we have a dedicated APN to our users. So in this case, we are like, I don't remember the taxonomy of the MVNOs yesterday, but we are kind of a skinny MVNO because we provide the call service, and for some users, we provide the APN service as well. We have a radio service as well. This is used for our safety, the safety people and that need to intervene in the tunnel. It's based on a standard which is Tetra. It's digital radio. We have 3 base stations, and here we have the full role of the operator. We keep the infrastructure and we provide the terminals to the users. And we even have a way of performing indoor localization to our users. So let's go to the interesting part, the telephony network. Today we have a network that is based on a PBX, let's say that is TDM and IP hybrid. So we have 4 main nodes that have another 17 second level nodes, and all of it is ensured by a double power supply with batteries that can last until 24 hours in some cases. Right now we have 12,000 fixed extensions. You can see here that most of them are still wired interfaces, so we are way behind the IP revolution, let's say. We have a lot of analog and digital ones. We have some link, that's and IP phones, but this is the standard for our PBX provider, so they are not really SIP. And then we have, we cannot avoid the faxes. We have some bread phones. These are the security telephones in the tunnels. And we even have some modems for special services. And the thing is that for our, in total, around 20,000 subscriptions, both fixed and mobiles, we provide different levels of access for outbound calls. So we provide only calls to CERN or to the local area or worldwide. And then there's a billing system involved in that. So you get it automatically in your payslip at the end of the month. And then we have a lot of changes, and we have introduced in the last years an automated self-service. So if you want to change your rights, you want to get a new phone, all that is done automatically, updated in the network, and that has released a lot of manpower to do engineering. We do around 1,000 changes per year. So as a special service, we have this integration with Link or Skype for business. We do least cost routing for outgoing operators. We have around 5 million calls per year. We still keep a switchboard and a service desk for IT support. And then one of the most important service is the red phones over there. You can see that actually they were bought from a museum because they don't have any active electronic parts. So anything that has some active electronic parts will melt with the radiation. So this is only an analog interface, and then in one of the safe places in the LHCs where we really have the active equipment. We keep some call centers as well for the fire brigade. This needs to be really redundant, and we have the ability to make calls from our radio terminals to our fixed network. So the project itself, it has been named TONE for Telephony Open Source Network Evolution. And our main goal is to replace the PBX, which is now at the core of the system, and add something that is software-based, that will help us reduce the hardware and license cost. We avoid being locked in with a vendor, and I really think that that will increase the agility to provide and the flexibility to provide new services. The goal itself is to be able to support WebRTC or SIP clients and remove all or most of the traditional phones. We will keep just those that are needed for safety reasons. So the architecture itself, well, we have a cluster front ends that are Kamailios, some backends that are Asterisk with a MariaDB. Then we are using Homer as well with a Kamailio capture server. And then we have a homebrew provisioning server that is getting all the data from our human resources database, from our network database, and it's automatically propagating it to every of the Asterisk instances in the cluster. We do DNS load balancing for discovering which Kamailio is the closest to our location. We have an SBC. This is something that is required by our mobile operator to send us the calls. And then Kamailio will be terminating also the WebRTC tunnels. Yeah, so the front end, it's Kamailio itself. It's just dispatching to the Asterisk server that is based on your availability zone. And it's doing all the protection part, ACLs, topology hiding, white and black listings. And then it will be a TLS and WebSocket termination layer. For the Asterisk part, it's the one in charge of identifying the calling user rights. So we are doing it based on context. We are doing the least cost routing there. Actually, it's calculated externally, and then we just input it to the Asterisk. And then we are providing the IVR service for our mobile VPN. When you want to make outbound calls, you get an IVR that asks you for some kind of credentials in order to do so. So we are doing this architecture with the help of the CERN's Agile infrastructure, which is using OpenStack as an infrastructure as a service solution. We are using Puppet for configuration management and Foreman as an instance lifecycle manager. All our repos are on a private GitLab instance, and we do continuous integration there, and we follow all the issues with Jira. So basically, we have the Puppet master that will know which kind of node is yours. In this example, it's a web server. And basically, you can add new hosts using Foreman or the CLI. So it will just ask Foreman, what kind is it, the server that you're trying to create. Then it will retrieve all the Puppet manifest from GitLab. And then it will just propagate it to the hosts that are actually managed by OpenStack. For the infrastructure as a service part, CERN opened a tender several years ago for doing a data center extension. So we have our main data center in Geneva, but now we have a secondary data center next to Budapest. They are connected by two 100 gigabit international links, which at the time I think it was a record-breaking speed. We have really low latency and stable jitter. So what we have done is we have created some backup domain in this data center in case our data center goes down. We are able to send some capacity to Vineyard, which is the name of the data center. So normally the DNS load balancer will point to only the Kamailios in Geneva, but in case of a disaster, we will be sending everything to Vineyard. And then there's this coupling between front-end and routing engine, or asterisk for that. And as well, the red part, we have added some bare metal services because the battery duration in the data center, I think it's around 8 hours. That should be enough for a normal organization, but for us, we really need to provide extended battery life, and here we are doing so. And then I just wanted to finish with how we define the the Kamailio installation with Puppet. Basically, you can define some variables. These are later overridden. And you can ensure that some packages are installed. Here we are listing all the packages that needs to be installed before Kamailio. Then we have our own way of storing secrets and passwords, so you can just add a root password for that, just for temporary installation, and then overwrite it after all the installation has been done. And then you can just create these exec functions where, well, we're just downloading it from the Kamailio page. We are just installing there. The unpack part is just a tar part that I omitted. And then we just install it, and you just provide the comments to the cell. So with this, we are able to install Kamailio in minutes and have it up and running and add more capacity to our cluster. So the project itself is now in its first steps. This year, we are providing the first service, which is the IVR for our mobile VPN users. We are doing it this summer. We are now with all the preparations. Next, of course, we need to place an SBC and have external SIP connectivity. And then we will start doing the massive user migration towards either SIP or WebRTC. And that's one of our biggest challenges, because we have a study group with our web developers, and we are trying to identify which is the best use case right now, to provide a SIP soft phone or just go directly to WebRTC clients. And then we have opened a separate project for being able to integrate the call center solution for the fire brigade into this architecture, and seeing how can we keep the same level of redundancy. So we will need to somehow ensure by batteries even the workstations for the fire brigade. So for that, we are looking for collaborators. So that's all. Thank you.
I'll have to put the first question, because when I saw the submission, my first thought coming in my mind was, can I get a SIP invite in the accelerator and see if Kamailio can catch it?
Maybe.
Okay, so now a real question here, as I could see interesting, and I'm okay, maybe not that much surprised given the roots of research that Kamailio has it. Research was always open to this new open source, which now it's no longer that new. But I'm glad that I see probably the most famous in the world, or at least in Europe, going open source, and seeing that many of the, like Asterix, Homer, are all involved. Did you find it kind of difficult to get it? Because researchers at some point, they care only, because I have other relatives in the research, okay, I study atomic physics, I don't really need to bother, and I expect that some different levels of management are still related to research. Were there like issues on proposing this and convincing this would be the right way moving forward?
Actually, I was recruited for that. That was why.
So you're not involved in it?
Yeah,
okay.
so it was an idea that had been long around the department, and finally they decided to do so. And there's always been a really good open source culture at CERN, so we didn't need to break any barriers in that sense.
Okay, I thought I could get a recipe that we could use it for other similar institutes, because sometimes they say, oh, I don't really want to bother with other things. I just want to focus on my, bits of research and don't want to maintain other things. Okay, so now we have a question there.
So this infrastructure is really quite critical for CERN, I assume. So is there any support contract, service level agreements with, for example, Digium for the Astros part, or with other companies, or do you all cover that yourself?
The idea is that the infrastructure will hold during the night, especially, which is when we don't have shift engineers. We will probably have that in the future, but we are actually doing kind of an overkill here. We are adding many nodes to the cluster, and each one of them is independent. So actually the probabilities of it just dying off the whole infrastructure in a certain moment are really low. Yep.
Okay.
Well, I saw the picture that you have some old devices. Does that mean that you really have to support the old IP version 4 protocol? Because I assume you only use IPv6.
Yes, for sure.
They still have some IPv4 left in the accelerator waiting to come out?
Yeah, that's some problem we need to address with the old devices. They are only IPv4 capable, and we will need to do the IPv4 to IPv6.
Yeah, that's a shame.
But the next new particles will be only IPv6. Okay, so thank you, Francisco. Really interesting and.